good morning. We start a bit late. Apologies for that. Thomas Nowak is still trying to figure things out technically. So this is why I'm the one who will introduce our lovely speakers today, and we will start with Thomas Lamiger, who will talk about first of all, to introduce him, Dr. Thomas Lamiger, actually. He studied chemical engineering at the Vienna University of Technology, where he received his diploma as well as his PhD in the field of mechanical process engineering. Since February 2020, he has been working as a system production manager at Agrana. At the end of May, he took over the internal project management of the dry efficiency project of Agrana and is responsible for the commissioning and integration of the heat pump demonstrator. So Thomas will present the heat pump demonstrator at Agrana with Start Factory in Pischeldorf, Austria. Thomas, thank you for joining. And you are already a presenter, so can you please share your screen?
Yeah. Hello to everyone.
Great.
I hope everyone can see my presentation.
Yes.
Thank you very much for your kind introduction. I just want to say 2-3 sentences about Agrana. Where the Agrana is an Austrian leading company which adds value to agricultural commodities to create industrial products for downstream processes. So the Agrana has more than 50 sugar, starch, and fruit production sites worldwide, and aims to rely on closed economic cycles and strives to optimize energy and energy efficiency. So therefore, Agrana is delighted to be part of the Dry Efficiency Consortium that is developing technology solution converting industrial waste heat into processes heat. At the Agrana Organic Refinery in Pischelsdorf, which is located approximately 50 kilometers west of Vienna. Since 2007, there is the Austrian largest bioethanol plant located, producing approximately 250,000 cubic meters per year of bioethanol. And since 2030, and the second wheat starch processing plant was just started at the end of 2019. We are also integrated here completely organic refinery now, producing approximately 260,000 tons of wheat starch and a lot of other valuable byproducts, as you can see here on the slide. And to increase the share of renewable energy, a novel closed-loop heat pump system was integrated in the starch dryer VSA1. As you can see here on the screen, the scheme of the starch dryer and the heat exchanger. The heat pump demonstrator was with a heating capacity of approximately 400 kilowatts, which is something around 10% of the total wheat starch dryer heat demand. It's integrated downstream water-to-air heat exchanger coming from our internal heat recovery cycle, and following this heat exchanger, this water, which has approximately 70 degrees Celsius, is used as a source for the evaporator of the heat pump. The heat pump itself supplies temperature in the range of 110 to 160 degrees by the condenser at our internal water circuits, which releases then here the heat to our heat exchanger, where we can save the steam followed, which is still necessary to reach a drying air of approximately 160 degrees Celsius. You can see here on the screen we are using here the dry air of approximately 160 degrees, 200 tons per hour to dry our starch from 34 to 40% moisture down to 10%. You have a total volume from approximately 40 to 50 tons per hour. On this slide, you can see the hydraulic scheme is shown on the left-hand side. It's a twin cycle configuration with two screw compressors, with internal suction gas heat exchanger and evaporator connected parallel, which also has the possibility to change it to a serial configuration. This configuration has considerable advantages regarding safety, startup, having more overall performance from very low to medium temperature lifts, which provides the highest COP up to approximately 4 at moderate temperature levels at the highest energy cost savings per year. So to bring all the necessary parts to our factory, a container outside the starch dryers is used for all the housing of the equipment, including all measurement and control systems. So the scheme you can see here, or the 3D scheme you can see here on this right-hand side picture. And on this screen you can see two pictures during installation in or at the end of September 2019, starting at the beginning of 2000. We had a little delay due to Corona, so we started the commissioning of the whole heat pump at the end of May 2020. On this slide, you can see the expected targets of primary energy reduction and CO2 emission reduction as calculated during the start of this project. So the primary energy could be reduced depending on the heat supply temperature by 20 to 80%, which would lead to around 2,200 megawatt hour per year as energy consumption savings. And concerning the CO2 emission reduction, could be up to 40 to 90%. In this case, it could be lead to a CO2 emission reduction of approximately 500 tons per year, depending, as I said, concerning the heat supply temperature. As I already said, due to Corona, we had a little delay. The commissioning is still ongoing. Together with our partners, AMT, IT, and Enertech, we're still in the commissioning phase. And as the project is recently prolonged till August 2021, an intensive test phase in the coming weeks and months will follow. We hope to be able to reschedule the demo event in 2021, and I'm looking forward to seeing you in Bischofsdorf. So thank you very much for having the chance here to be as a guest speaker at this webinar.
Thank you. And thank you for presenting our project too. That was very important for this webinar. And I'm also very happy that Thomas is here with us.
Good morning. Thank you very much, and welcome everybody. And sorry for the delay. It was a technical glitch, which I expected when I was a child in the 21st century wouldn't happen, but they do. I guess we all know about that. So Thank you, Sabina, for opening the event in my absence. Thank you, Thomas, for giving that presentation. You have been introduced already. I was supposed to give a short overview on the relevance of the topic, and I think it's very timely to have Dry F as the opening speech, because the industrial heat sector is by and large overlooked in European policy. We have discussed that many times with policymakers. Many of the pieces of legislation that are so easily adaptable and applied to residential and commercial or residential and office buildings, they don't apply to industrial buildings. And when it comes to heat pumps, it's actually even worse, because then the general opinion is held that heat pumps cannot do anything in industrial heating because they're simply not good enough and they can't provide the high temperature levels that are needed. And inside the heat segment, you have pointed to the drying segment, which is probably one of the biggest ones that is accessible to heat pumps. But we will discuss that in the questions and answer period. We are having quite an engineering heavy panel. Let me just introduce the other speakers. We have Erik von Oossanen, who is an energy and mechanical engineer from Rotterdam University and is now working for Trane. You can see him to be very international if you look at the back of his room with a world map. So maybe these are all the countries where you can use industrial heat pumps. And Erik is also responsible now for Trane's applied product portfolio. So he's also a bit of the future thinker for Trane, if you can say that for this segment. Then we have Soledad van Eijk, who is, I guess, really an innovator, a business developer for TNO, the Dutch Research Institute. And the Dutch Research Institute has very obscure types of projects where they do sound heat pumps and magnetic heat pumps. And if you're, I'm quite into the technology, but with these technologies that you are doing research on, Soledad, I'm sometimes also lost. So I'm very, very much looking forward to your presentation, how to connect innovation to products in the market, especially when it comes to the reduction of CO2. And you're also an engineer, a chemical engineer, which I understand is even harder than mechanical engineer. So now the mechanical engineers can bash me for that. I don't know. I'm not an engineer, as you can see already, so I have no sensitivities for the difficulties of that field. And then we have Robert Unsworth, who is working for GEA for 28 years now, also very international, has been traveling the globe for the company. And he will speak later to us on the heat pumps for repurposing the industrial process waste energy. And actually, a colleague of you, Robert, has once said to me, we have made the problem that we are encountering today ourselves, because we told everybody that they should just put hot vapor pipes, steam pipes into their production lines, and then they can do everything with steam. So if you want to cook a coffee into an industrial facility, you would just make a steam pipe connection to that, boil the water, and then you have coffee, even though you could also take a coffee maker. And he said, this colleague of yours, I will not name him, but he said once to me, this is something that we really have to address, and we have to look at how much energy do we really need for a given industrial process. So I hope that we will shed some light on this situation today with all these experts. From the housekeeping perspective, could all of you that have questions that occur to you while listening to the presentations, put them into the questions and answer box, and then we will put them into the Q&A session at the end of the presentations. Good. Maybe the last thing I should say that we have done some statistics, because also statistics for large heat pumps is not so easy to get to, and we know that around the industrial heat demand is around 2,500 terawatt hours, and about 10% of that we think, as EHPA, and we have done that in our large heat pump working group, we think about 10% of that amount, so 180, maybe 200 terawatt hours, can be provided by the heat pumps on the current level of technology. And we will hear from you what is possible, and maybe you can also comment on that. Is that a proper assumption, or do you think the heat pumps can even do more over the next 10, 20, or 30 years? Okay, so then we continue. I would like to give the floor to Erik first, who will talk about what I just said, using heat pumps to repurpose industrial process waste energy. And he will present to us a case study on that. Erik, please.
Yeah, thank you. going to show my screen.
Yeah, visible.
Good. Okay. So first of all, thank you for the opportunity to share our experiences and path towards using heat pumps in process applications. So I'm going to walk you with a brief introduction of how the technology is being implemented and how the technology is addressing different ambient conditions in Europe and also different processes in Europe. And then dive into an example of a project that has been fulfilled and that is proving that heat pump application in process systems can drastically improve the system efficiency of those processes. So I'll quickly go to the next slide. And initially, as an introduction to the technology matching different requirements, I chose to show you the applications that can be used in different ambient conditions. So initially, heat pumps are always thought like being used to source energy from ambient sources. So that's ambient air, or it is water sources. And ambient air, as we know, across Europe, depending on the climate, can vary a lot at winter time. So dependent of those climate conditions, there are different ways to attach the heating process to the ambient source. And to give a bit of understanding, so we know that air-to-water heat pumps are commonly used across the Mediterranean areas. And that's for the reason why, because that's where the ambient temperatures allow an easier access to the energy of air by an air-to-water heat pump. When it gets colder, that becomes more complicated, and on top of that, you want to have a higher temperature to heat the system. So if you go to the top, you can see that when it's very low temperature, ambient temperature, we see water-to-water heat pumps being used more often, as they are not dependent of the low ambient temperatures at the peak of the heating season, and have a much better efficiency by sourcing from any liquid that typically is above 0 degrees Celsius. And then to reach high temperatures for heating, and high temperatures is relative. So our technology, we are talking about temperatures up to about 85 degrees C. Many options are there, and one of those options are to cascade energy from an air-sourced heat pump to a water-to-water booster, so that at the end you are not limited to the limitations of an air-to-water heat pump, which typically can create about 55 degrees, but you can also increase the temperatures in areas, for instance, the green-colored countries where you want to have heating, you can source from the air, but you want to have heating at 85 degrees for more conventional heating systems. So this is just a brief introduction when you would source from the ambient conditions. Now, there's another way to source energy, and that's by reusing energy in a process, and that's where the introduction to process heating kicks in. So initially, it's very common that as a traditional approach, that cooling and heating are being seen separately. So there's a heating process being supported by any fossil fuel combustion, and then there's a cooling process which typically is taken care of by a chiller. And we many times, more than 90% of the times, we see these processes still being disconnected. So there's heating and there's cooling, and there's no combination between those systems. They work independent of each other. Now, this has been a very common approach for many years, and for process applications and also data centers, by the way, that have a wintertime cooling need, we started to improve those efficiencies by creating free cooling, right? It's a common known theme. Free cooling, in fact, it's about opening the windows when it's cold outside. So you're still combusting the fossil fuel to create heating in one side of the process or the building, and on the other end, you're opening the window so that you have free cooling where you want to have cooling at winter conditions or lower climate conditions. And it is improving the efficiency. And by the way, I did not mention it yet, but TER, it's standing for the total efficiency ratio. In fact, it's a ratio between the energy creation for use of heating and cooling and the energy consumption for that heating and cooling. So the energy consumption for cooling gets reduced when free cooling kicks in. And now with the electrification of heating, we start to have more discussions to combine the two elements of heating and cooling within the same process. And by doing that, we are diminishing the use of the fossil fuel combustion and connect the dots of heating and cooling. And in fact, we use everything that the cooling process is asking for as a heating source to reduce the consumption of that fossil fuel. And in this example, and it depends on the temperatures, the efficiency can go up. It's very normal to have an EER of 4, so a COP of 5, which is the balance between cooling and heating and the energy consumption. And if you use both, then you have the 5 and the 4 together, still with that one power input, which generates a 9 at the end of the day. And that gives a real indication of the efficiency increase you can gain if you connect the dots well at the right temperatures in a process system. So that's the theory, and now I want to step into the practical experience. So this is just one of the many projects that we faced, and this is in France, where an animal health product company was seeking for opportunities to improve their efficiency, and they started talking with us because they initially were thinking of improving the efficiency by improving the cooling process. But in general, they want to really optimize the resources they use across their processes. And so the initial discussion that we had with them was to improve efficiency of chillers, because that's what we are initially known for. And but you know what's commonly known, I think, is that by innovations over the last 5-6 years, we doubled the efficiencies, especially the seasonal efficiencies of systems, of cooling systems. So there's a huge gain already to be achieved when you would replace an old existing unit, chiller unit, by a new chiller unit. But during that discussion, we also started discussing and discovering the potential to connect the dots of the heating and the cooling. And at the end, when we could identify the heating and the cooling opportunities that were in that process, we could see that the energy gain would be much higher than just the doubling of efficiency by the cooling plant itself. So that's what we did, and we approached this from a standpoint, an initial standpoint of a disconnected cooling and a disconnected heating system. So that was the original plant. There was this air-cooled chiller. This is an older style air-cooled chiller that needed to be replaced. And again, the efficiency of that unit would potentially double by the new innovations. And then we had the heating plant that was disconnected and using fossil fuel to heat. Looking at the profile of the process, it looked a little bit like a comfort cooling process, but there were constant cooling requirements, and there were at winter time. You can see that this was southern France, so between 0 and 10 degrees, there was still cooling requirement there, and also at summertime there was still heating requirement in the same plant for the process applications. The heating temperatures that were required were about 60 to 80, and the cooling requirement required were 11 to 6. So we removed the disconnection. So we connected the dots of the heating and the cooling by a water-to-water heat pump system. In this case, it's a parallel system. Many times we also use a serial connection. And by using this system, we were able to provide the cooling at 6 degrees and the heating at 80 degrees with one and the same system. And at summertime, when needed, these units can run as coolers only when it would really be needed. But we know from the load chart that there's always a need for heating in the same building. So the old system, or the boiler system, did not need to be replaced. We suggested to keep that as a backup. It always makes sense to keep this as a backup for two reasons. One is you never know when more heat is needed, and it doesn't take an investment to keep what you have. And second is at the moment that temperatures would become more severe or higher temperatures would be needed, and sometimes that is what happens, then it can still make sense to have additional fossil fuel heating available, but you still reduce a lot of the energy consumption by connecting the dots across the year. So that is a lot of energy reduction, even though you sometimes need to have the capacity of the fossil fuel at extreme conditions. So wrapping this up, by when we looked at it halfway the year, so this was about 50% of the annual consumption, we did see a huge reduction as per the expectation. So the expectation is also expected to be fulfilled during the rest of the year. And that means that it's about a 50% reduction of energy consumption. So the energy ratio went up from 1.18 to 2.15, so that's almost double. And consequently, the annual gas consumption decreased by about 80% by connecting those dots for the capacity that we could cover with this system. And at the end of the day, the avoidance of CO2 footprint was quite impressive with 225 tons. And that is only by opening up the discussion from a simple chiller replacement to connecting the dots and creating a heat pump system in this process system. So at the end, thank you for this. This is how we think to reduce the energy intensity of the world. And with those innovations, we believe that there's a lot that we can create together with customers in the process industry. Thank you. I hope you're still with me.
Thank you, Erik, for this interesting presentation. We will look at this with some questions in the Q&A session. I think one thing that strikes me is that if you need cooling, you get heat for free. If we could establish that sentence in many people's brains, then I guess we would see more of these integrated solutions in the future. We will continue immediately with Robert, who will talk about some heat pump applications in food and beverage. And I have to say, I'm particularly keen on listening to the latter, because I really have tried to get people to use heat pumps in distilleries, in vineyards, in breweries, and the examples are rather small. So, Robert.
Hi, hopefully you can hear me. Yeah, just a brief explanation. I'm a lowly mechanical engineer, so thanks for that, Thomas. Yeah, GA, nobody ever heard of GA, and I certainly hadn't, but we, different divisions within GA, make breweries, dairies, food plants, blood plasma plants. So just some statistics: every second litre of beer, every second litre of milk, and every third chicken McNugget comes out of a GA plant. So, but again, nobody's ever heard of us, but they're busy peddling away in the background. And personally, I studied brewing in Copenhagen years ago, and I always thought it was bizarre, because I've always been in refrigeration, that you walk into the refrigeration plant and you're normally in a cooler climate, you see lots of steam coming off of the condenser, and generally right next door there's a boiler house where you've got tons of smoke coming out the top of the stack. And I just thought it was really bizarre that the two didn't get put together. So if I carry on with the presentation, hopefully we can see how we can actually change this. So just some basics. Our customers pretty much have the same need. So the top line, you can see the poultry guys. You know, the chicken goes in feeling happy and warm at 38 degrees. The first thing they do is they defeather and eviscerate it, where they use heat to open up the pores and take the feathers off. And then the bird then gets chilled, it may get portioned, it may get frozen, but it leaves cold. They use a boiler for heating it up, and they use a refrigeration plant for cooling it down. Likewise, in the milk side, the milk goes in, hopefully at 2, gets pasteurized, the refrigeration guys go and chill it, and then again it goes to storage and cold distribution. Vegetables, as an example, they come off the field, they get blanched, washed around 80 degrees, and normally they go off for freezing. So you can see all of the heat going in via a boiler, and then the heat being removed again via the refrigeration process. If we just take the refrigeration process as an example, this is just a simple flooded ammonia system where the heat in around about -6 is 2.6 megawatts. We add the power of compression, and both get rejected at the condenser up on the roof. So we're rejecting around about 3.1 megawatts of heat. The only issue is the heat's not really at a useful temperature. If we wanted hot water at 30 odd degrees, we could just swap the condenser, but nobody really needs a lot of heat at 30 degrees in these factories. So if we have a look at an enthalpy diagram, we have the heat going in at the cold end. We have the power going in to the compressor to raise the pressure and condensing pressure. Then we reject the heat at around about 30 degrees or whatever our ambient is, but it's still heat. You know, I always tell our clients that heat's heat, whether it's -40 or if it's 140, it's all energy. So what we do now, we add the compressor, which is boosting that heat to a useful temperature. So now we've got it up to 70 degrees, so we can actually start using it for doing things, pasteurization, this sort of thing. And we've only added a little bit of power to do so, as opposed to, you know, converting the heat to electricity means we can do it with a sustainable way, and I can show you an example of this in a minute. So, but yeah, the energy in this case is coming in from a windmill, as opposed to having to use a lot more fuel, even if it is clean coal, like our American cousins think. You're using a lot more compared to the amount of power to raise just by raising the temperature of the heat you require. Some examples of this, again, if we go back to one of our poultry plants that we've done, you have the boiler chugging away, producing hot water. These guys use a lot of hot water at night time in a refrigerated environment. The factory's a fridge, basically. It's also sprayed onto the birds and at around 52 degrees. And then the birds are cooled down and go into cold stores, etc. If we map the amount of energy that we're putting in, that's equivalent to 11 million kilowatt hours for heating, 3.9 million kilowatt hours for power for the refrigeration side. So combined, nigh on 15 million kilowatt hours per year and 4,000 tons of CO2. What we did there, we just basically added the heat pump to boost the heat that we normally reject via the condenser, which allowed us to turn off the boilers, or it allowed us to turn off 3 out of 4 boilers and half of the condensers, because we're no longer rejecting the heat. So if we then look at the revised figures, we're now only using 0.8 million kilowatt hours a year for the electricity for the heat pump. The refrigeration's about the same. We've reduced fans, but raised in the heat pump power. But the combined total has dropped significantly. So it's 10 million kilowatt hours per year and nigh on 3,000 tons of CO2. If we just have a look at the client's own information, we shoved a great big buffer tank in, and actually that was reused from an old dairy. Actually, it's an old dairy tank of 350 cubic meters. The 4 boilers, 2 of them immediately switched off, and the other 2 reduced down to 50% loading. So we saved them 3/4 of their fuel consumption. If we have a look at the same thing in a dairy, the milk comes in at the top. It normally comes in from the farm. Well, they'd like it at 2 degrees, but it normally drifts up to 5. So they have an intake chiller. So you cool it back down, and then the lower 3 heat exchangers, that's the pasteurizer. So they have a recovery rate on a pasteurizer where the warm or the cold milk coming in transfers heat to the hot milk leaving, and they're normally 90–92% efficient, which means you have to inject heat to get the milk up to the pasteurization temperature, which on milk is about 72 degrees, or fresh milk or cream 74, 76, something like this. But the process is whatever you put in kilowatts, and let's say it's a megawatt, you have to remove that megawatt at the other end via the refrigeration process. And it's the same thing. You got your boiler putting the heat in and the refrigeration plant taking it out. Again, sticking in some figures, it's 3.7 million kilowatt hours of fuel for the heating and 750,000 for refrigeration. And because we were using evaporative condensers in this case, it was 21,000 cubic meters to reject that heat at the evaporative condenser. Here we added a booster heat pump, so basically recompressing the gas up to 82 degrees, making a 82-degree water loop, and just sticking a 3-way valve in to blend it into the pasteurization loop. The reduction, again, 3.4 million kilowatt hours per year and 650 tons of CO2. This is the latest project which we are working on at the moment. It's currently being installed, and here it gets a little bit less GEA, but it's 4 million bottles of juice per year by a company called Innocent, and the concept, well, that's my idea of explaining to a client how heat works. But the important thing about any of these processes is understanding the process and the heat map. We call it a heat map. It's knowing what's getting heated up to what temperature and what needs cooling down. The problem with the traditional form of heating, you buy a boiler and it's a 10-bar boiler, so you chug along with 160 degrees worth of steam, and irrespective of what you use that heat for, whether it's in this case, I mean, this is truly idiotic of this process, but so I'll explain it quickly. You have juice pulp coming in from South America that someone's taken the trouble to freeze, and they stick it through a tunnel in which they inject steam to melt the ice. So that's equivalent to you taking a bag of frozen peas out at home, switching the kettle on and hanging them above the kettle to defrost. But on an industrial scale, we seem to think that's appropriate. Then you have the usual culprits running around spraying everywhere with hot water whilst you're trying to refrigerate the area. You have the pasteurization, and juice is normally pasteurized around 85 degrees, and the end product is 2. So it goes into storage at 2 to 4, and then it's then distributed at that point. So explaining this in my sketch form, my comedic form, the heat's going in and we're removing it again here, and the refrigeration plant's rejecting 8.5 megawatt. Again, it's just not at the right temperature. So it's easy to boost that heat at 8.5 megawatts back up to a useful temperature. So again, we put in recompression, take it up from 35, or the portion from 35 up to the temperature which we need. This is a simplified version of it, and I'll show you what we really did, because we split the heat streams, which is really important. So it enabled the client actually not to put a boiler in at all. So this factory is going to be one of the, well, I think it's the world's first production factory, juice production factory, with no boiler. It's all being recovered heat, the whole pasteurization and heating process. This is, let's say, more of a schematic that's appropriate than my bamblings as comics. But so here you have air conditioning, which is the air conditioning of the factory, and some water chilling. You have the process cooling with the green pipes and a buffer tank. The buffer tank is to take the spikes out of the process before it hits our refrigeration plant. You can see the compressors here, and then we reject the heat via some condensers up on the roof. But in this case, we're only rejecting around about half of the heat, because the other half is being desuperheated, compressed up to 65. So, and this is what I meant by heat mapping, and I'll show you why in a second. But we have a hot water buffer tank at I think it's about 380 cubic meters from memory, for 65-degree water for the heat that we can do at a lower temperature level, and then we go up to 90 degrees on the final CIP and pasteurizing temperatures. So we're producing 90-degree water here. But again, we're recompressing up from 60 up to 90 to achieve that. So yeah, it's multi-stage compression, really. This is another way of doing it. So these ones are for food process factories, where they produce ready meals, pasta, and that sort of thing. Again, we're doing cooling with some cooling chillers, and we're doing heating with heating chillers. But in effect, the heating chiller, which is cunningly coloured red, is in parallel with the heat rejector. So when we have a heat requirement, which is the buffer tank on the left-hand side, we just boost it up, and in this case it's 70 degrees, and then therefore only rejects the excess heat from the refrigeration process. But you can do it as a stage like this, which actually is more efficient, because you're recompressing the same gas up, or we're going through a heat exchange at this phase. But perfectly, they're both perfect examples, and much better than people historically produce heat. And this is the reason why. So if you compare this with a boiler, so again, we go back to our chugging boiler at 10 bar that's making steam at 160 degrees. A boiler, whether you take heat up, so you take the example of the juice where they melt the ice, they melt the ice to produce +2 degree juice. They do that with steam at 160 degrees. I mean, that's madness. So what we do, we say, okay, well, we need heat, but as we go up in temperature, the efficiency goes down. So it's important, if half your heat is, let's say you've got a megawatt requirement at 65, you can do with a COP of 10 and a carbon reduction of 91% compared with a boiler. Going up to 90, we do with a COP of 3.7. And most of our clients, you still have a very high CO2 reduction, but most of our clients have to see a return on investment. So we map this against gas. So depending on the region and the cost of electricity to gas, we get what we call a spark gap. So as long as the spark gap means that our COP for heating is around about the same, most of our clients will go for this option, which limits the temperature of this technology. And this is ammonia. But obviously, we look at other refrigerants and producing hotter temperatures. But I think as the processes increase and this technology becomes more normal, then it will be applied to higher and higher temperatures. And the easiest way to explain what we do to our customers are to say, well, if you think about the heat we take out of your product when we put it in the refrigerator at home, if you connected the back of your refrigerator to your oven, then the heat that you're taking out in your refrigerator is the heat that you're cooking the stuff in the oven or attached to your hot water pipe. So I hope I haven't gone on too long, but yeah, we'll have some questions no doubt at the end. But we're doing this a lot at the moment, and it's becoming more and more the way to go. So thank you.
Super, Robert, thank you very much. I was still missing the brewery, but maybe we can have that in a bilateral discussion, because we have tons of questions now and we still have one speaker, Soledad, tonight. Don't feel pressured. Connect for us the dots from innovation to product, and then we go into the Q&A session. If whoever wants, since it was partly my fault, I at least have 5 or 10 minutes more to go through the questions. I don't know if the other speakers can offer the same. But if those of you that could stay a bit longer, then that would be helpful to answer some of the questions from the audience. Soledad, please.
Thank you, Thomas. I'm just checking. I think you see not the full screen, right? I have to...
Presenter view. Yeah, not the full screen.
Yeah. Okay. So I know now how to switch that. So I guess you see. So now you see the good one.
Yep.
Yeah. Thank you, Thomas. So thanks for the introduction. And well, I'm going to tell something about the high temperature heat pump developments that we're doing at TNO. And for the people who are walking around a long time in the heat pump industry, you might know the research I'm presenting better under that it's been done by the company ECN, which was the Dutch Energy Research Center of the Netherlands, but we are now merged with TNO. So it's the same work, but under a new name. So quickly on TNO, you already said it, but quickly. So TNO is applied research organization. And basically what we do is we connect knowledge to and innovation to boost the competitive strength of the industry and society in a sustainable way. And over 3,400 people work there every day to do this in very different fields. So not only on heat pumps. So that is on TNO. But so what's the reason why it's so important for Institute as TNO to work on a topic like this? And it's been addressed already a lot. If you look at the Netherlands, more than 1,200 petajoules of energy is being used every year just in the industry alone. And of this, a great portion, 550 petajoules, is used for heat. So if you can make this heat more sustainable, you're actually making a huge impact into sustainability goals of the industry. Then this is a picture with a lot of data, but and you don't have to read it all. But what this shows is actually this heat is not being used at one temperature. Right? So if we're talking about heat in the industry, we're talking about from basically room temperature to processes that go up to 1,500 degrees in Celsius. So there is not going to be one solution to make the heat supply in industry sustainable. But if you make this picture a bit more simple, you can see that there's different sectors operating in different windows, and there the processes are more similar. So you can work with sector approaches, and especially for the temperature up to 200 degrees, heat pumps are very interesting and a solution to look at. So what is the portfolio TNO is working on? And Thomas, you named it very exotic solutions, well, or something in that trend. So, but if you're looking at the left bottom, so here this is the one where we're historically strong. So low temperature heat reuse. So we're looking at compression heat pumps, the thermoacoustic heat pumps. So this is the sound heat pumps to say, and the sorption heat pumps, heat storage, and steam compression. What we're also starting to do as a research organization is to look at the technologies that go to higher temperatures. So to look at thermoelectric conversions, for instance, or to reuse heat at higher temperatures. And also we're looking a bit at the supply. But what I want to focus today on is the low temperature heat reuse. So and then I'm talking to 200 degrees around this temperature. At TNO, we're developing, and especially on the compression heat pumps and not on the other ones. And why the compression heat pump? Because I think this one is really close to the market and close to really being used in the industry. And so while we are doing at TNO also a lot of the, let's say, newer stuff, in the end, our goal is to really make an impact and also get these technologies being used in the industry. So I want to focus on the compression heat pump developments. It started with the Catch It project, where we developed a heat pump with working fluid butane, which generated 120 degrees of steam at capacity of 200 kilowatts. So first we tested this at TNO, but this one was also demonstrated in a paper mill from Smurfit Kappa to show that we actually could produce steam at these temperatures. And from this, we're taking actually two development routes. At the one hand, we're trying to really push the boundaries of the temperature that you can reach. In the STEPS project, we switched to pentane as a working fluid to go up to 150 degrees of Celsius. And now in Encore project, we're looking at real new media to go to even higher temperatures with a compression heat pump and to show that you can generate steam up to these temperatures. The other thing we're doing is going to larger scale. So I call it here TRL, but actually it's larger capacities. And in the low capex and in the Fuse project, we're actually want to we're making 2 megawatt heat pumps and want to demonstrate that you can actually make them already and produce steam at these temperatures. And these are the two projects that I would like to show you a bit of the technical, let's say, so where we are and how we are approaching this. So starting with the low capex project, on the pictures you see the heat pump that is being developed in the low capex project. It's a heat pump, as the name low capex is suggesting. It is really the aim to try to make a heat pump with the lowest capex that is currently possible to achieve. And we're doing that by really looking at what can we already purchase from the market to build a heat pump. So we're not trying to do R&D in the way that we're developing components ourselves in this case, but we're trying to work together and connect a heat pump with the existing equipment. So this heat pump that you see here, so here it's being towed in, and on the lower picture you see it installed in the lab. So the black part is the heat pump, and behind it, the more, let's say, aluminium silver colored is the actual infrastructure that is gonna generate waste heat to be able to operate the heat pump. So with this heat pump, we're going to produce steam at 120 degrees C and at 2 megawatt scale. We're using synthetic working fluid, an HFO. And actually in this design, we're still, there's two compressors and it's constructed parallel on the high pressure side. You can actually see the gray cylinders that are the top of the two compressors, and they share an evaporator. So actually, the design we have now, we actually think that there's even potential to future lower the cost of the capex even more if we would be able to make this one compressor and one evaporator. But in this project, this was now the best option to go for. So this heat pump is being installed right now. It was the intention already to have it tested at the TNO facilities, but due to COVID, all the installation took a bit longer. But we're expecting to have the first results of this heat pump this year to show that it's actually running and working. After we demonstrate it in a controlled lab environment, it is the intention to also really demonstrate this heat pump at industry. And for this case, the idea is to demonstrate it in a paper mill, and the paper mill of Smurfit Kappa. So this is on the low capex project. Then we have the Fuse project, which is actually a step up. This project is still a bit in earlier phase, but the intention of this project is to produce steam at 150 degrees using 2 megawatts, also at the 2 megawatt scale. We're using natural working fluid for this one. It's going to be pentane that we're using, and the aim is to take waste heat from 60 to 90 degrees and bring it up to this 150. And also here, although we are really trying to reduce the investment cost, because we think this is very important to reduce this investment cost as much as possible for the future implementation of heat pump technologies. The current challenge for this project is finding a suitable compressor to use. So this is currently an ongoing search, which we're doing to find a compressor for this to build this heat pump. But that's the part of the R&D project, and I think that's we will find it and and we will be able to build the heat pump here. Also, this heat pump will first be tested and proven in the lab environment that we have at TNO, and then it is meant to be demonstrated at Dow Chemical to produce steam of these temperatures. Quickly, something on what I'm saying is that we're actually on the Carnot lab, on the facilities we have, because I think this is a new thing, not shared a lot yet, is that we're actually at PET built a new facility to actually be able to test heat pumps up to 2 megawatt, because we see that that showing in a controlled environment that actually heat pumps works really helps to convince end users to go into these demonstration phases. So this is the Carnot lab we built. So there's several heat pump test facilities also for smaller heat pumps, but we can test heat pumps up to 10 megawatt with an output of 10 bar steam. We can use flammable working media, so the lab is suitable for that, and there's a 1 megawatt electrical connection. And apart from this, there's also some other topics, like there's a humid air loop and a hot air loop, so that we can also simulate some industrial other processes. And so we built this not only to test our own, so let's say, heat pumps that we're developing, but I think it's very important for innovation on heat pumps and getting them implemented in general, that we work together in Europe and as companies. So these facilities are also available for people who would like to first demonstrate something in a controlled environment. And that's coming to my last slide, because as a research organization, it's it's also asked lots of what do we see, what is needed for further innovation. And I think Thomas Nowak already mentioned that currently there's not a lot or maybe no attention for EU policymakers to really get also industrial heat pumps more on the picture. And I think the way to go there is work together. And what we did, as with other research organizations in Europe, is write a white paper, which actually is addressing this topic. So what is the need? Why do we need to focus on this? I will not go into detail on this white paper. I just wanted to mention that it's out there. You will get the links, so then you will also, the slides, I guess, so you will also be able to get the link. And if you really want to know more about the white paper, then on the 29th of October, there will be a webinar that is going into the detail of this. But the message is working together is key. So I want to end with that. So thank you. And
very interesting, Soledad. And actually, you're closing it and you're bridging to the Q&A very nicely. I would have said that this white paper is probably enough material to do a whole series of online seminars. So I'm surprised to see that you tried to put it all into one session. That's going to be a challenge. You said something very interesting, and I think in the sense of time, that is, we will just drop some of the questions that we have prepared and look at this. If I listen to all of you, my immediate response would be, why are people not queuing? And that's also something that is obviously a question that the audience has. I have a number of questions here where people say, but what stops industry from using all these great solutions? Robert, you have said it. There is really many factories and many processes that run exactly like that. Erik, you have said it. Thomas, I think from dry efficiency, we don't even have to say it, because it's the nucleus of that project. So why can't we go faster, in your opinion?
In my opinion?
All of you, but yeah, go ahead.
Okay, yeah, I can quickly say something on the challenges I see from an R&D institute, right? I think there is two things that we see, and that's one, that you're really interfering in an existing, in an existing system. So there's something that is very well known and works well, you're putting something new there. So I think there is some reluctance there, and therefore I think these demonstrations really are key. And I think in the end, costs always is, so the capex versus the opex is something that is, it really has to be beneficial for organizations to step in. But that's what I see.
We can have the others. Do you see it the same way, Thomas, Robert, Erik?
Yeah, I think one of the reasons why is also the isolated approach of the industry, right? So what I mentioned in the presentation that I gave is that it started off by, can you improve the chiller performance, right? Because we want to replace the chiller, without thinking of the connecting these dots between the cooling side and the heating side of the same process. And you don't always need to be at the end of the lifetime of the combination of the boiler and the chiller to make the combination and create a heat pump opportunity. So I think it's mindset, it's new technology that people are not thinking of. So we need to open the eyes of customers and help them understand it's not difficult. And to an element, it's comfort zone, right? There's a lot of buzz about, will heat pumps reach the temperatures that we need? But then it turns into the question, what temperature do you need? And that also resonates to what Robert mentioned, right? If you want to use steam for everything, including the coffee machine, including defrosting things, why would you want to do that, right? We are in a new century where you can think differently.
I think one of the problems history, we've been burning shit to heat things up since we sat outside caves thousands of years ago. And then someone comes along and says, this refrigeration plant's going to give you heat. And all of our clients think refrigeration does cooling. And we're just as bad, because our refrigeration people talk about cooling, they don't talk about heating. And generally, when the clients are building their new factories, they look at their process first. It's production process first, and we need a boiler. And they go and buy all that kit way before they start talking about refrigerating it again. And the example I gave with Innocent, that was really because we got in early and just, I joke about the comic, but it is a joke. Why do you defrost stuff with steam? So as soon as the client understands that and is willing to take the first step, they'll go with you. But most of our clients, and that's all of us, have existing buildings with a rusty old boiler in the backyard, and to convert to pressurized hot water and a heat pump, it's quite an investment. So the return on investment is not so good. So we need to get the capital investment down. And to be honest, the governments need to help as well. So here's another rant. In the UK at the moment, you can get a grant for sticking a borehole in the ground and providing heat from cooling worms, but you can't get a grant by recompressing gas up from a refrigeration system, which is 3-4 times more efficient than sticking a ground source heat pump in. So, there's a lot of things that have got to happen, but this is a relatively new area for everybody to get their heads around. Most of our clients just want to make chickens. They don't care really how it gets heated and how it gets cooled. But over time, that's all going to change. So there's definitely going to be a massive upsurge in the next 10 years. I mean, as people build new factories, they'll have heat pumps, not boilers. That's just it. We can do it now. So
that could be the closing remark, but we have another question that I still would like to give you some attention. Or maybe first, Thomas, what is your opinion on this topic? What is stopping people from having more heat pumps in industrial processes? No.
I hope you can hear me now. Yeah, concerning our expectation we had so far from the dry efficiency project, we see the advantages having this heat pump. Only we have in this demonstrator just 10% of our wheat starch dryer to put in as an additional heat source. We have seen it's very successful to have this heat pump there, and we also have already decided to bring this system to other dryers, because we see the advantages. Even as we already had, the investment costs are still high, but concerning perspectives in terms of CO2 consumption, prices, etc. Yeah, we at the Trane, we're looking forward to have more of such heat pumps as we reach now temperatures levels which are very interesting.
So you would say from a client side, you have changed your position a little bit, and now you're moving more into the direction of more heat pumps. So it supports what Robert says. New factories get heat pumps.
I don't know if in new factories, but I know at the production side in Pischelsdorf, we're thinking about installation. We have already done some pre-adjustments in the new factory to be able to bring a heat pump at the new factory as well. Yeah.
Okay. Quick round on a second topic that is making the audience very nervous. What about the refrigerants? What is typically used, and do you see the F-gas regulation as a limiting factor of the further deployment of heat pump technology? That would again be a question to all of us. And maybe you can combine it with a closing remark, because even though I would have more time, I don't want to stretch your patience too long.
Yeah, if I may start, Thomas, we see the HFO opportunity as an opportunity for heat pumps because it comes with much wider operating maps. The rather standard technology that typically is being used for cooling systems can allow temperatures up to about 85 degrees with HFOs. So it's an opportunity rather than a risk, right? It's helping rather than pushing against the options that we have. So we are ready for this F-gas reduction. We see HFOs being used across the board in Europe, and all applied systems are ready to use that and to take the benefit of those HFOs to reach higher temperatures. So we welcome that.
Okay.
I'm going to
continue with Robert.
I'll throw the opposite argument in. Go green. So natural refrigerants. So, but again, you know, I don't live in a world where I need 200 degrees. When you're cooking food, beverage, juice, we're in the low 100. So so we can use CO2, we can use isobutane, pentane. You know, we don't need to be using HFO in my area. I do understand the HFO side because generally it's a cheaper solution, but yeah, we're pushing CO2, and again, it's understanding the process. If it's a recirculatory system, you need to use a different technology. If you're injecting steam into a product, you can use CO2. So yeah.
But maybe we can touch on that a little bit further. What is the technical boundaries of these refrigerants? Because if we look at more than 200 degrees centigrade, a colleague said that would be water vapor compressed. So can we either with HFOs or with green natural refrigerants go to 180, 200 degrees today? Or is that future music where we need something else?
I think on an industrial scale, where we're talking megawatts, I mean, Soledad's working in that area. She should comment, but I think it's a little way in the future, but it's achievable. So
yeah, I must agree with it. You know, there's a reason why it's one of the R&D projects where we're looking at. So we're looking at different refrigerants that could go to these temperatures, and we think it's feasible. So it should not stop it. So they are out there. We just need to check how it works. But it is indeed still an R&D topic. But the moment you find a refrigerant like that, there's no reason why you can then not quickly implement everything you know on the lower, let's say on the 120, 130 heat pumps that you're already going, that we are building now at 2 megawatts to apply the lessons on these refrigerants to the heat pumps that we know. So it can go quick, but it's still indeed an R&D topic.
Okay. For you as a user, Thomas, is the F-gas that is used a decisive criterion, or is the functionality more important?
from our side, we see the advantages, and I cannot say that we are looking for some alternatives. Also, in our consortium, we're still looking forward to research and development of other gases. But concerning Agrana, we stay what we have, and we're looking forward to still use EHPA.
Okay. Well, thank you very much. It's 11:30, so we have taken some more time for questions and answers. This was very interesting. To the overall audience, if you want to join us for a similar webinar or online seminar on large heat pumps, then we have the number 12 seminar next week on the 8th of October on large heat pumps in district heating. I guess it is the same machine, just a different application. So we don't heat up the produce, we heat up the buildings and the cities, and we cool it down at the same time. So again, we will see efficiency gains from the joint use of heating and cooling. Don't forget, if you need cooling, you get heat for free. And that makes economic sense and saves the environment. Thank you very much for today. Thank you all my presenters here. That was very interesting for me. And the high attendance rate shows the same. We had more than 130 people in the peak. Thank you very much and have a great rest of the day.
Good. Thank you. Bye, guys.
Thank you. Bye-bye.
Bye, everyone.